High Wycombe, England. 24th of July, 1943. 2100 hours. In the operations room of RAF Bomber Command, colored strings stretched across a wall-mounted map, marking routes that would converge on Hamburg. Staff officers moved quietly among the tables. On this night, navigators would carry something new: bundles of metallic strips, each 27 centimeters long, 2 centimeters wide. The strips had been tested for months. Both sides possessed the technology. Both sides had held back, fearing retaliation. Tonight, that restraint would end. Arthur Harris, Commander-in-Chief of Bomber Command, had authorized Operation Gamara. The orders were clear: release window continuously over the target. Controllers expected radar-guided defenses to track individual aircraft. The reports would soon show otherwise. The cheapest material in the war, thin foil cut to precise lengths, was about to collapse Germany's night fighter system. The experiment would not be conducted on a range. It would be tested over a burning city. The plotting room was dark except for the glow of cathode ray tubes. Night shift. Western Europe, 1940 through 1943. A Luftwaffe operator leaned over a grid map, marking tracks with a grease pencil. Another operator pressed headphones tight against his ears, relaying bearings. The voices were calm, methodical. Outside, in the cold North German night, radar antennas turned slowly, sweeping invisible beams across the sky. General Joseph Kamhuber had built this system, the Kamhuber line, a network of radar boxes stretching from Denmark to the Swiss border, each box a Himmelbett, a flak bed, designed to control a single engagement. The concept was elegant. Freya early warning radars, operating on very high frequency bands around 2.4 meters wavelength, detected incoming bombers at ranges between 100 and 160 kilometers. When a contact appeared, the information passed to Würzburg gunlaying radars, smaller, more precise sets operating at 560 MHz with a wavelength of 53 centimeters. The Würzburg could track both the bomber and the night fighter simultaneously, providing range, bearing, and altitude with enough accuracy to vector the fighter onto an intercept course. The system required perfect coordination, detection to tracking to interception. Each step depended on the previous one. Ground controllers spoke continuously with pilots, adjusting headings by degrees, calling out ranges that closed from 5,000 meters to 3,000 to 1,000. When conditions were ideal, sparse traffic, clear skies, functioning equipment, the system worked. Night fighters claimed steady victories over the Ruhr during 1942 and early 1943. But the system had a fundamental assumption. It assumed distinguishable, trackable returns. It assumed that each radar echo represented one aircraft moving through one box at a time. It assumed the relationship between electromagnetic reflections and physical objects remained direct, predictable. The operators did not yet know that the very physics that made radar powerful, metal surfaces reflecting radio waves, would soon make it vulnerable. An aircraft's aluminum skin returned a signal. So would anything metallic of the right dimensions, tumbling slowly through the night sky. Across the North Sea, British scientists understood this principle perfectly. They had known since 1942. Malvern, United Kingdom. August 1942. A test rig stood outside the telecommunications research establishment. A receiver scope sat on a bench, its trace glowing green. An engineer climbed a gantry, holding a bundle of metallic strips. He released them. The strips caught the wind, separating, fluttering. On the scope, the trace spiked sharply. Multiple returns, bright and persistent, from objects no larger than a man's hand. Joan Curran watched from below. She had been working on this problem for months: how to saturate enemy radar with false returns. The physics were straightforward. A conductor cut to approximately half the wavelength of an incident radio wave would resonate, returning a strong echo. The Würzburg sets operated near 53 centimeters. Half of that, 26.5 centimeters, became the target length. During control trials aboard Wellington bombers, bundles of these strips produced scope saturation. Multiple contacts where only one aircraft existed. The radar could not distinguish real from false. The telecommunications research establishment forwarded its findings to the Air Ministry. The technology worked. It was cheap. Production would be simple, just aluminum foil cut and packaged. But London hesitated. If Britain used Chaff against Germany, Germany would immediately copy it against Britain's own defenses. The chain-home radar network protecting British cities would face the same problem. Mutual deterrence kept both sides silent. The British called it window. The Germans, independently testing the same concept, called it double. Both nations possessed the key to blinding enemy radar. Neither dared use it first. Through 1942 and into 1943, the bundles remained classified under most secret. Meanwhile, bomber command losses mounted. Deep penetration raids into Germany saw 7 to 8% losses. Rates that, sustained over months, would hollow out entire squadrons. Each percentage point represented hundreds of aircrew. Briefing rooms grew quieter. Replacement crews arrived at stations, met their new aircraft, and flew their first mission over the Ruhr. Some did not return. The statistics were cold. The mathematics were clear. Without a change, the bombing campaign could not continue. Arthur Harris pressed for authorization. His argument was direct. The losses were unsustainable. If Chaff could reduce them, even temporarily, it must be used. The decisive first use had to be overwhelming, enough aircraft, enough Chaff, to prove the concept before Germany adapted. The Air Ministry finally agreed. Operation Gemara would be the test. Not an isolated sortie, but multiple raids in rapid succession, each one releasing window in quantities sufficient to saturate the entire defensive network. The experiment would measure not just technical effect but operational impact. Could Chaff collapse the night fighter system? Could it buy time, weeks, perhaps months, before countermeasures restored the balance? The decision was made. The first raid was scheduled for late July. Distribution began. High Wycombe, July 1943. The operations wall displayed colored string marking routes for Operation Gemara. Staff officers pinned tables next to the bomb load manifests. Each Lancaster would carry 48 bundles of window. Navigators received specific instructions. Release one bundle every minute during the approach, increasing to one every 30 seconds over the target. The goal was not deception in the traditional sense, not fake aircraft in fake locations, but saturation. A continuous corridor of reflective material trailing behind the bomber stream, drifting with the wind, creating a broad zone where radar could not resolve individual contacts. The mathematics of the plan were precise. Each bundle contained approximately 2,000 strips. A force of 746 bombers, each releasing 48 bundles over 2 hours, would deploy more than 71 million individual reflectors. These strips would fall slowly, roughly 360 meters per minute at 18,000 feet, remaining aloft for nearly an hour. The result would be a sky filled with millions of resonant dipoles, each one returning a signal indistinguishable from an aircraft. Pre-Gemara loss rates averaged 7 to 8% on deep penetrations. Analysts had calculated the cost. 7% of 700 aircraft meant 49 aircraft lost. 49 crews, 343 men, per raid. Over a sustained campaign, the numbers compounded. Squadrons could not maintain operational strength. Training programs could not replace losses fast enough. Something had to change. Air Ministry directives warned that Germany would adapt quickly once Chaff was revealed. The enemy would modify radar sets, change frequencies, develop filter circuits, shift tactics. The British advantage would be temporary. Therefore, the first use had to be massive and immediate, giving no time for German controllers to develop countermeasures before the second and third raids followed. The operational logic was ruthless. Exploit the surprise completely, then accept that the window of advantage would close. The name itself, window, reflected this understanding. An opening. A brief one. On the 24th of July, ground crews loaded the bundles aboard the Lancasters and Halifaxes. The packages were bulky but light, thin foil and paper backing, sealed against moisture. Each package was stamped, "Most Secret." Operational use authorized navigators stored them near their stations, checking that chutes were clear for release. Some crews asked what the material did. The answers were vague. New countermeasure. Follow the release schedule. Drop continuously. Trust the plan. The bombers began engines at twilight. One by one, they taxied to the runways. The sound of Merlins rose across the English countryside, a low thunder that became routine for those who lived near the airfields. By 2200 hours, the main force was airborne, assembling in streams, turning east over the North Sea. The navigators checked their stopwatches. In an hour, they would begin releasing the first bundles. The radar operators in Germany, watching their scopes, did not yet know what was coming. Neither did the night fighter pilots, sitting in their cockpits at Lüneburg and Stade and Hanover, waiting for vectors that would guide them into the bomber stream. The experiment was underway. The Freya scope at Stade lit with returns. 2250 hours. The operator leaned closer. Contacts were multiplying, not in orderly progression but in broad clusters. The range rate marks, used to distinguish moving aircraft from static clutter, failed to resolve coherent tracks. The pips spread across the screen like ink in water. The operator keyed his microphone, reporting to the Luftwaffe Commando 11 plotting center. Controllers marked the positions on their maps, but the marks became meaningless. Where was the bomber stream? Everywhere. Nowhere. The grid filled with symbols. At Cuxhaven, another Freya operator experienced the same phenomenon. His screen showed returns at ranges from 80 kilometers down to 40, spreading across a 30-degree arc. He attempted to track individual contacts, marking their positions at intervals, calculating heading and speed. The calculations failed. Some returns appeared stationary. Others drifted at wind speed rather than aircraft velocity. Still others moved erratically, jumping between range gates. The operator reported to his supervisor. Equipment functioning normally, but returns inconsistent with known bomber characteristics. The supervisor examined the scope himself. He recognized immediately that this was not equipment malfunction. The returns were real electromagnetic reflections. They simply did not correspond to aircraft. The Würzburg sets fared worse. These radars, designed for fire control, required precise tracking to vector night fighters or direct flak batteries. Now their displays showed dozens of returns where one should appear. An operator at Cuxhaven attempted to lock onto a target. The return faded, reappeared elsewhere, split into two contacts, merged again. The tracking data was incoherent. He reported loss of lock and tried another target. Same result. A third attempt produced similar failure. The operator's training emphasized persistence. If initial acquisition failed, try different gain settings, different scan rates, different tracking modes. None helped. The problem was not technique. The problem was environment. The sky itself had become unreadable. Searchlight crews, waiting for radar guidance, swept their beams across empty sky. Flak batteries fired into approximate zones, but the patterns lacked the precision that came from radar-derived altitude and bearing. The shells burst far from the actual bomber stream. Battery commanders, watching the barrage, recognized the signs of blind fire. The usual tight patterns, concentrated boxes tracking bomber altitude and speed, were absent. Instead, shells burst randomly across wide volumes of airspace. Some detonated at 15,000 feet, others at 20,000. The spread indicated lack of precise fire control data. The guns were firing on estimates, not radar solutions. The physics were working exactly as intended. Each window strip, measuring approximately half the wavelength of the Würzburg radar signal, resonated and returned a strong echo. The strips fell in clouds, hundreds per bundle, thousands of bundles released every minute by hundreds of aircraft. The result was a moving wall of false contacts drifting eastward at the prevailing wind speed. The Himmelbett system assumed one target per box. Now each box contained hundreds of targets. The sequential handoff process, detection, tracking, interception, broke at the first step. Radar could still detect. It could not track. In the plotting centers, controllers attempted to salvage the situation. Some tried to ignore the brightest clusters, hoping real bombers existed at the edges. Others vectored night fighters toward areas of highest density, reasoning that bombers must be somewhere nearby. The fighters launched, climbed, and circled, asking for fresh headings. Controllers provided estimates, but each vector led to empty sky or more confusing returns. The cycle time, the interval required to detect, identify, track, and intercept, stretched from minutes to impossible. A night fighter might reach an indicated position only to find nothing, while actual bombers passed kilometers away, unseen. The Luftwaffe had prepared for many contingencies: jamming, spoofing, electronic deception. But not this. Not saturation by reflective material so simple that its production required no advanced technology. The metal strips cost almost nothing. They required no power source, no guidance, no control. They simply fell, slowly, reflecting signals. The contrast was stark. One of the most sophisticated air defense networks in the world, paralyzed by aluminum foil. German post-action reports later characterized the interference as reflections. Not yet, noise jamming analysts recognized the problem immediately. The returns were real, not electronic noise, but they represented nothing of tactical value. The operators could not assign height, heading, or speed to most contacts. The data stream overwhelmed human capacity to process it. Even with functioning equipment and trained personnel, the network could not provide actionable intelligence. The system's organizing logic, sequential handoff from detection to control, collapsed when the input became statistically saturated. Night fighters launched. Vectors no longer led to bombers. Aboard a Lancaster, call sign Sugar Charlie, the navigator checked his kneeboard timer. 2310 hours. He reached for the first bundle of window, opened the chute, and released it. The package disappeared into slipstream. He noted the time in his log. Countermeasures deployed over the next hour. He would release 47 more bundles at timed intervals. The wireless operator monitored frequencies, listening for German controller chatter. The broadcast circuits, RT channels used to coordinate night fighters, carried confused traffic. Voices requesting clarification, requests for new vectors, gaps where silence replaced the usual crisp commands. In the rear turret, the gunner scanned the darkness. On previous missions to Hamburg, searchlight activity had been intense, vertical columns forming cones, creating illuminated killing zones where fighters could spot bombers easily. Tonight was different. A few searchlights probed upward, but their movements seemed random, unfocused. They swept broad arcs rather than converging on specific points. The gunner reported this over the intercom. The pilot acknowledged. Unusual, but favorable. The bomb aimer, lying prone in the nose, watched flak bursts through the perspex. He had flown 12 missions. He knew the difference between radar-predicted and barrage fire. Radar-predicted flak formed tight patterns, shells bursting in boxes that tracked the bomber stream's altitude and speed. Controllers adjusted firing solutions continuously, walking the barrage through the formation. Tonight, the flak was scattered. Shells burst at varying altitudes across wide areas. Some detonations were close enough that fragments rattled against the fuselage, but most were distant. The pattern suggested guesswork rather than calculation. The main force, approaching from the North Sea, maintained formation. Crews expected searchlights, vertical columns of white light forming cones over Hamburg, creating a box of illumination where flak could fire with visual reference. Instead, the searchlight belts were sporadic. A few beams swept the sky randomly, unable to fix on targets. Flak bursts appeared, but the patterns lacked the concentrated barrages typical of radar-directed fire. The shells exploded in broad, scattered fields rather than tight boxes tracking the bomber stream. The window was working. Each Lancaster, each Halifax, released bundles continuously. The strips separated in the airstream, spreading into clouds that drifted eastward and downward. At 18,000 feet, the material fell roughly 360 meters per minute, remaining airborne for nearly an hour. By the time the last bomber crossed the target, the sky behind contained a corridor of chaff tens of kilometers long and several kilometers wide. This corridor moved with the wind, creating a zone where radar returns were meaningless. Controllers could not distinguish bombers from reflections. Fire control systems could not achieve tracking lock. Bomber command crews, briefed on window but uncertain of its effect, noted the difference. Over the North Sea, defensive reactions seemed muted. Over Hamburg itself, the flak was lighter than expected. Not absent. Shells still burst, fighters still climbed, but the coordination was gone. The radar-guided boxes that usually formed dense killing zones now fired blindly. Bomb aimers completed their runs with fewer evasive maneuvers. The usual intensity of defensive fire, calibrated by radar to intercept altitude and speed, was replaced by area barrage effective only by chance. The Operational Research Section at Bomber Command Headquarters tracked losses through the night. Radio operators at bases in England noted which aircraft checked in after crossing back over the North Sea. The preliminary counts arrived before dawn. 12 aircraft missing from the main force. 12 from 746. Loss rate, 1.6%. On previous raids to Hamburg, loss rates had exceeded 5%. The numbers were stark. A major raid, deep penetration, heavily defended target with single-digit losses. The analysts cross-checked the figures. No error. The window had performed beyond expectations. Debriefing sessions began after the crews landed. Navigators confirmed continuous release. Pilots reported reduced defensive fire. Wireless operators described confused German radio traffic. The consensus was immediate. The chaff worked. Whatever radar-guided systems the Germans employed, they could not function under saturation conditions. The strips created clutter too dense for controllers to resolve. The mathematics were simple. Millions of reflectors overwhelmed thousands of operators. The human element, the controller interpreting scope returns, the pilot following vectors, became the bottleneck. The system could not scale to the input level. The second Gemara raid was already scheduled. Same tactics, same countermeasure. The brief window of advantage before German labs developed filters before doctrine adapted would be exploited fully. Harris authorized continuation. The orders were clear. Use window on all subsequent raids. The material was cheap, production was ready, the effect was proven. The night war over Germany had shifted. Not ended, but shifted. For a few weeks, perhaps a few months, radar-guided defenses would struggle while both sides raced toward the next adaptation. In the night fighter control rooms near Lüneburg and Hanover, the situation remained chaotic through the 25th, 26th, and 27th of July. Pilots launched, climbed to patrol altitudes, and requested vectors. Controllers attempted to provide headings, but each intercept cycle failed. The bomber stream moved through defended zones while fighters circled uselessly, separated by kilometers from their targets. Fuel ran low. Fighters landed, refueled, launched again. The cycles repeated without result. The Himmelbett model, dependent on one engagement per box, could not adapt. Each box now contained dozens of apparent targets. Würzburg operators attempted to prioritize returns based on signal strength or movement patterns, but the chaff clouds drifted unpredictably. A strong return might be a Lancaster or a dense concentration of falling strips. The operators had no method to distinguish them. The doctrine assumed clarity. It received confusion. Major Hajo Hermann, a night fighter tactician, proposed an alternative. Wild sow, wild boar, abandon radar control entirely. Instead, send single-engine fighters Bf-109s, FW-190 over the target cities where they could hunt visually by firelight. The burning city would illuminate the bombers from below. The fighters would operate independently, using their eyes instead of radar. It was a crude solution, trading precision for chaos. But when precision was impossible, chaos became viable. The doctrine was approved and implemented rapidly. Fighters began arriving over Hamburg during subsequent Gemara raids. Some claimed kills, bombers silhouetted against flames, vulnerable during bomb runs. But the tactic carried costs. Friendly flak, firing blindly upward, threatened the fighters as much as the bombers. Coordination with heavy anti-aircraft batteries was minimal. Fighters occasionally fell to their own side's fire. Weather also limited effectiveness. If clouds obscured the city, or if smoke rose too thick, visual contact became difficult. The method worked only under specific conditions. Zomsau, tame boar, followed as a modification. Radar control was not abandoned but loosened. Instead of precise vectors to individual bombers, controllers directed fighters into general zones where the bomber stream was likely. Once there, pilots used airborne radars, Neptune sets, to acquire targets independently. This approach reduced controller workload but required fighters equipped with functioning airborne sets and pilots trained in their use. Not all were. The shift represented a fundamental doctrinal change. The Himmelbett concept relied on centralized control, precision, and sequential processing. Wildsau and Zomsau relied on decentralization, approximation, and pilot initiative. The new tactics survived, they produced kills, but at the cost of the system's original organizing principle. Radar no longer provided the dominant advantage. It became one tool among several, often the least reliable. The invisible eyes that once saw everything now saw only clutter. German night fighter reports recorded the breakdown. Pilots described confusing controller instructions, failed intercepts, and wasted fuel. Ground personnel noted radar sets functioning normally, transmitting, receiving, displaying returns, yet producing no usable intelligence. The problem was not equipment failure. It was saturation. The system's capacity, measured in trackable contacts per hour, had been exceeded by an order of magnitude. No amount of operator skill could process the input. The human nervous system, hands adjusting controls, eyes reading scopes, voices issuing commands, operated at a fixed rate. The Chaff arrived faster. The Luftwaffe adapted by surviving. New tactics emerged through trial. Some crews learned to ignore the clutter and focus on rare clear returns. Others accepted lower accuracy and higher losses. The defensive network continued to function, but it no longer functioned as designed. The elegant integration of radar, control, and intercept gave way to improvisational chaos. Victories still occurred, but the kill rate fell sharply. The percentage of bombers destroyed per raid dropped from 7% to 3%, then to 2%. The bombing campaign could be sustained. Before window, it could not. The shift in those percentages represented thousands of lives. Aircrew who flew missions and returned because radar had failed to vector a fighter onto their tail. The strips of foil, tumbling through the night, had measurable effects. Not symbolic. Actual. Quantifiable. The war continued. But the terms had changed. At Peenemünde and Rechlin, German engineers worked urgently through August and September of 1943. Test ranges activated. Würzburg-Ries operators experimented with modified sensitivity time control curves, adjustments that might suppress near-range clutter while preserving distant returns. Engineers sketched filter networks on graph paper, proposing circuits that could discriminate between rapidly falling chaff and slower, steadier bomber tracks. Doppler shift analysis offered one approach. Chaff fell at terminal velocity. Bombers flew horizontally at cruise speed. The velocity signatures differed. In theory, filters could separate them. In practice, implementation proved difficult. Doppler discrimination required coherent processing, measuring phase shifts across successive radar pulses. The existing Würzburg sets were not designed for this. Retrofits would require new transmitters, new receivers, or entirely new radar systems. Development time stretched to months. Meanwhile, the raids continued. Each night, more window fell. The engineers worked faster, but they were racing against an adversary with unlimited production capacity for the simplest possible countermeasure. Some improvements emerged. Operators learned to adjust pulse repetition frequencies, changing the timing of transmitted pulses to reduce clutter density on certain scope presentations. Conical scan modifications allowed radar beams to sweep small circles, helping distinguish stationary clutter from moving targets. These adjustments trimmed the worst effects. Experienced operators occasionally regained tracking capability against isolated bombers. But the core problem remained: saturation. When the sky filled with millions of reflectors, no filter could extract signal from noise without drastic sensitivity reduction. And reducing sensitivity meant missing real bombers. British countermeasures evolved in parallel. RAF analysts anticipated German adaptation. Window strips were produced in multiple lengths, targeting different radar frequencies. When intelligence indicated German radars shifting to new bands, new Chaff variants appeared within weeks. Mandrel jammers, airborne noise transmitters, joined the electronic order of battle, adding broadband interference to the reflective chaff. Later, H-2S ground mapping radars aboard Pathfinder aircraft provided navigation while also radiating signals that further complicated German defensive pictures. The technical competition accelerated. Each side introduced modifications. Each modification prompted a counter-modification. German technical notes from autumn 1943 reveal the frustration. One report concluded that saturation, not merely deceptive tracking, was the fundamental issue. The problem was not equipment quality or operator skill. It was capacity. The network could process a finite number of returns per minute. The British exceeded that limit by releasing reflectors in quantities 10 times greater than the network's design threshold. Hardware fixes could improve margins. They could not unsaturate a sky filled with metal. British production scaled effortlessly. Foil was abundant. Cutting machines operated around the clock. By September, output reached tens of millions of strips per week. Packaging shifted to centralized facilities, then distributed to squadron-level stores. The logistics were trivial. Each bomber carried several kilograms of chaff, negligible compared to bomb loads measured in tons. The material cost per strip was measured in fractions of a penny. The effect on enemy defenses was measured in percentage point reductions in bomber losses. The cost-benefit ratio was extraordinary. The cheapest consumable in the war had become a capacity weapon. Archival records preserve the German assessment. One staff officer's correspondence, later captured, paraphrased period phrasing, "Our eyes remain open, yet we see nothing." The metaphor was apartment radar still functioned. Antennas rotated, transmitters pulsed, scopes glowed. But the information presented was unusable. The difference between signal and noise had collapsed. The Luftwaffe responded by dispersing effort across multiple sensor types: visual observation, acoustic detectors, radio direction finding. No single system replaced radar's former dominance. The network became less a precision instrument and more a collection of approximate methods, each contributing partial information. Integration of these sources required more personnel, more time, more coordination. The defensive response became slower, less accurate, less lethal. The mathematics were unforgiving. Saturation scaled linearly with production, but processing capacity did not. Every night, millions more strips fell. Every night, controllers struggled. The balance had shifted. It would not shift back. In London and across the Midlands, factories retooled for window production. September through November of 1943. Bales of pre-cut foil stacked in warehouses, ready for loading. RAF lorries departed with crates marked "Window Most Secret" until operational use. The secrecy designation remained even after deployment because precise dimensions and release procedures still offered intelligence value. But the material itself was no longer secret. Germany knew. Britain knew. Both sides used it. The race now was production capacity and tactical integration. Critics within the Air Ministry had initially expected supply bottlenecks. Aluminum was precious. Cutting millions of strips to precise tolerances seemed logistically complex. In practice, neither problem materialized. The foil required was thin, far thinner than aircraft skin or structural elements. Production did not compete with aircraft manufacturing. Cutting was mechanized. Roller presses with templates, producing thousands of strips per hour. Packaging became routine. Bundles wrapped in paper, sealed against moisture, stacked in crates. The Ministry of Aircraft Production coordinated centralized cutting, while the RAF Supply Directorate handled distribution to forward bases. By autumn 1943, output exceeded 100 million strips per week, sufficient for dozens of major raids. Squadrons maintained local stocks. Ground crews loaded bundles aboard bombers as routinely as flares or incendiaries. The once exotic countermeasure became standard equipment. Navigators released window without special orders. It was simply part of the mission profile. Take off, form up, activate H-2S, release window at intervals, drop bombs, return. The Chaff merged into operational procedure. Operational statistics reflected the effect. Night fighter kill rates, which averaged 7 to 8% in early 1943, fell sharply after July. By September, average loss rates across all deep penetration raids dropped to 3%. By November, approaching 2% on some missions. The Operational Research section published analyses correlating window use with reduced losses. Route planning and improved H2S navigation also contributed, but Chaff was the dominant factor. The difference was measurable in lives. At 7% losses, a 30-mission tour had a 50% survival probability. At 2%, survival probability exceeded 90%. The shift was not marginal. It was transformative. Aircrew morale improved. Squadrons reported higher re-enlistment rates. Experienced crews completing tours sometimes volunteered for additional missions. The constant attrition, watching aircraft fail to return, seeing empty bunks in the morning eased. Not eliminated. Losses continued, but the trajectory changed. Before window, the mathematics pointed toward unsustainable attrition. After window, the bombing campaign could continue indefinitely. Strategic effects followed. More bombers reached targets. More ordnance fell. German industrial output, already strained, faced increasing disruption. The air war's balance shifted not because technology advanced, radar remained fundamentally the same, but because a simple countermeasure neutralized that technology's advantage. German correspondence from the period reflects the shift. Staff officers reported frustration. Luftwaffe commanders requested more fighters, more radar sets, more searchlights. But quantity could not solve a qualitative problem. Adding more radars meant adding more confused operators. More fighters meant more pilots circling uselessly. The system's bottleneck was not resources but physics. No amount of effort could overcome saturation when the saturation source was unlimited. Logistics enabled routine use on every mission. Not a surprise weapon deployed once for shock effect, but a standard tool used continuously. The RAF accepted that Germany would adapt. Filters would improve. Doctrine would shift. Airborne radars might mitigate some effects, but adaptation required time. Each week of delay was a week of reduced losses. Each month was thousands more sorties completed. The window of advantage, anticipated to last weeks, stretched to months. By the time German countermeasures matured, the air war's momentum had shifted decisively. Window had not won the war, but it had ensured that Bomber Command could continue fighting it. That continuation, sustained over years, mattered. The strips of foil, falling through night skies over Germany, represented more than electronic deception. They represented operational persistence, the capacity to endure, the ability to sustain effort against prepared defenses, the transformation of attrition from inevitable to manageable. The mathematics were cold. The effects were real. The conclusion was unavoidable. Saturation worked. The introduction of window forced both sides into rapid evolution. Germany developed new radar frequencies, attempting to move beyond the bands most vulnerable to chaff saturation. Centimetric radar, operating at wavelengths around 10 centimeters or shorter, offered one path. These higher frequencies required smaller chaff strips, complicating British production. But centimetric radar sets also required more advanced magnetrons and waveguide components. Manufacturing capacity lagged. By the time production increased, the British had already introduced new chaff variants targeting the new frequencies. Airborne interception radar improved. Neptune and later Liechtenstein SN2 sets gave night fighters independent search capability, reducing dependence on ground control. Fuji 212 and Fuji 220 systems incorporated limited frequency agility and automatic tracking. These sets performed better in cluttered environments, but they did not eliminate the problem. Chaff still degraded performance. Operators still struggled to distinguish real returns from false ones. The advantage shifted from overwhelming to partial, but partial was sufficient. Bombers continued releasing window. Fighters continued to struggle. Defensive doctrine adapted more successfully than technology. The Luftwaffe accepted that centralized, radar-directed interception was no longer viable as the sole method. Wild sow operations expanded, placing single-engine fighters over target cities where they hunted by firelight. Zom Sow placed twin-engine fighters in bomber stream zones, using airborne radar only after visual or electronic intelligence cues narrowed the search. Radio countermeasures operators aboard some night fighters monitored British H-2S transmissions, homing on those emissions rather than relying on ground radar. The system diversified. Redundancy replaced precision. Multiple imperfect sensors replaced one theoretically perfect sensor. These adaptations reduced the effectiveness of window but did not negate it. British loss rates rose slightly from their post-July lows. 2% climbed back toward 3%, occasionally 4% on heavily defended targets. But the rates never returned to pre-window levels. The statistical floor had shifted. The defensive network had learned to function in a degraded environment, but it functioned less effectively than before. Bomber Command maintained operational tempo. Raids continued throughout 1944 and into 1945. The air campaign that might have been throttled by unsustainable losses instead persisted to war's end. The Chaff concept proliferated. United States Army Air Forces adopted window for daylight raids, though with less dramatic effect. Daylight visibility reduced reliance on radar. Pacific theater operations used chaff against Japanese radars, achieving similar saturation effects. By 1945, every major air force employed some form of radar countermeasure. The technology became ubiquitous. What began as a closely guarded secret in 1942 ended as standard equipment by 1945. The knowledge diffused across all combatants, then into post-war arsenals. Modern militaries continue to use chaff. The strips are now packaged in expendable cartridges, automatically deployed by aircraft under threat, but the underlying principle remains unchanged. Saturate hostile radar with reflective material. Force the adversary to process more information than their systems can handle. Simple, cheap, effective. The strategic lesson was clear. Capacity weapons, those that overwhelm adversary decision-making or processing rates, could be as decisive as precision weapons. The strips of aluminum foil deployed over Germany in 1943 did not destroy radar sets. They rendered those sets less useful. The cumulative effect, thousands of missions flown with reduced losses, was strategically significant. Bomber Command survived its crisis. The night offensive continued. German industrial capacity degraded under sustained attack. Post-war analyses debated the bombing campaign's overall effectiveness, but none disputed that window was essential to sustaining the campaign. Without it, losses might have forced a suspension or redirection of effort. The course of the air war and perhaps the war itself would have developed differently. Technology races rarely end. Each innovation prompts a counter-innovation. Window did not permanently blind German radar. It forced adaptation. The adaptations did not restore the pre-window status quo. They produced a new equilibrium. The race continued into the Cold War, driving radar development, electronic warfare, and stealth technology. The conceptual lineage runs from window to modern chaff, jamming, and low-observable aircraft. Each generation applies the same principle. Deny or degrade adversary sensors. The methods grow more sophisticated. The goal remains unchanged. In the final year of the war, the electronic environment over Europe became extraordinarily complex. British bombers deployed window, mandrel jammers, and airborne cigar voice jammers simultaneously. German defenses operated multiple radar types across numerous frequency bands, coordinated through backup communication networks when primary channels were jammed. Both sides introduced new systems monthly. The pace of innovation was relentless. Each technical advantage lasted weeks before countermeasures appeared. Yet beneath the complexity, the fundamental dynamics established in July 1943 persisted. Radar remained essential but vulnerable. Chaff remained simple but effective. The balance shifted repeatedly, but never returned to the pre-window baseline. The night fighter force adapted, survived, and occasionally achieved local successes. But it never regained the systematic dominance it held in early 1943. The Himmelbett concept, elegant, centralized, precise, was obsolete. The replacement systems were messier, more distributed, and less effective. The Luftwaffe fought on, but fought uphill. For the aircrew, window became invisible. Not because the Chaff itself was invisible, it was highly visible on radar, but because its use became routine. Navigators released bundles without conscious thought, the way drivers shift gears. The countermeasure that once seemed exotic became part of the background, noticed only when absent. After the war, veterans recalled missions, targets, losses, close calls. Few remembered window specifically. It was just there. Always deployed. Always assumed. The strips fell every night, year after year, accumulating in fields across Germany. Thin foil mixed with soil, gradually corroding, eventually disappearing. Physical artifacts of an electronic war. Post-war technical assessments confirmed the operational impact. Studies by the United States Strategic Bombing Survey and British Bombing Survey Unit analyzed loss rates, correlated them with countermeasure deployment, and concluded that window reduced losses by approximately 4 percentage points on average across all missions where it was used. 4% of 700 aircraft was 28 aircraft per mission. Over 2 years, thousands of aircraft. Tens of thousands of aircrew. The numbers were approximate, many factors influenced loss rates, but the trend was clear. Window saved lives. Not dramatically, not individually, but statistically across large numbers. That was sufficient. The engineers who developed window received little public recognition during the war. Secrecy restrictions remained in place until after 1945. Joan Curran and the Telecommunications Research Establishment team continued working on other projects, cavity magnetrons, centimetric radar, proximity fuses, contributing to a cascade of innovations that defined mid-century electronic warfare. Their work on Chaff was one project among many, significant but not unique. The culture of secrecy that surrounded wartime research meant individual contributions often went unacknowledged. The systems worked. The campaigns succeeded. The names behind the systems faded into classified files. Germany's parallel development Doppel followed a similar path. German researchers independently derived the same principles, tested the same concepts, reached the same conclusions. The Luftwaffe held back for the same reasons the RAF did: fear of retaliation. When Britain deployed window first, Germany responded within weeks. The symmetry was striking. Both nations possessed the knowledge. Both hesitated. Both eventually used it. The technology was not proprietary. The physics were universal. Any nation with radar expertise could develop Chaff. The question was not capability but willingness to accept the consequences of first use. The consequences, once accepted, proved manageable. Radar adapted. Doctrine adapted. The war continued. Neither side gained permanent advantage from window alone. But the first use, Operation Gemara, July 1943, created a discontinuity. A sharp break in loss rates, a forced evolution in tactics, a demonstration that even sophisticated systems could be saturated by simple means. The lesson transcended the specific technology. It was a lesson in capacity, in thresholds, in the limits of processing speed versus input volume. Those lessons remained relevant long after the chaff strips stopped falling. They remain relevant today. The principles that made window effective, simplicity, mass production, saturation, continue to shape electronic warfare. The physics have not changed. The foil still falls. The radar still struggles. The story begun in 1943 continues in different forms, different frequencies, different conflicts. But the underlying reality persists. There are limits to what any system can process. Exceed those limits and the system fails. Window proved it. The proof endures. High Wycombe, May 1945. The operations room at RAF Bomber Command fell quiet. The maps on the walls showed the final dispositions. Germany had surrendered. The last mission had flown. Ground crews began demobilizing. Aircraft were stored or scrapped. Bundles of window, millions of strips prepared but never used, filled warehouses. Some would be kept for study. Most would be destroyed. In the years following the war, historians and analysts examined the bombing campaign's effectiveness. They debated targeting priorities, civilian casualties, strategic impact, and moral dimensions. The debates were complex, contentious, and ongoing. But within those debates, Window occupied a clear position. It worked. It reduced losses. It allowed the campaign to continue when continuation seemed unsustainable. The statistics were unambiguous. The cause and effect relationship was direct. Chaff saturated radar. Saturation reduced defensive effectiveness. Reduced defenses meant fewer losses. Fewer losses meant sustained operations. The logic was linear. Arthur Harris and the Bomber Command leadership understood this. So did the aircrew who flew the missions and the ground personnel who loaded the bundles. The strips of aluminum foil had not ended the war, but they had helped sustain the effort that contributed to its end. That contribution was real, measurable, and significant. Not mythical, not symbolic, quantifiable. The saved aircraft could be counted. The surviving crews could be named. The effect was tangible. For the Germans who operated the radar networks, the experience was frustrating but instructive. The Kammhuber line, once hailed as an impenetrable shield, had proven vulnerable. The lesson was humbling. No system is invulnerable. Every technology has a counter. Every defense can be saturated. The search for absolute security is futile. Adaptation is continuous. The race never ends. Those lessons shaped post-war radar development, electronic warfare doctrine, and strategic thought. The Luftwaffe's experience with Window informed decades of subsequent research into radar resistance, filter design, and sensor fusion. The knowledge was bitter, learned through defeat, but it was thorough. Joan Curran and the telecommunications research establishment team returned to peacetime work. Some continued in government research. Others moved to universities or private industry. The radar expertise developed during the war, chaff, magnetrons, antennas, signal processing, seeded entire industries. The electronics revolution of the mid-20th century drew heavily on wartime innovations. The engineers who developed Window contributed not just to military victory but to technological foundations that outlasted the conflict. The chaff itself, scattered across Europe in quantities beyond counting, gradually disappeared. Rain dissolved the paper backing. Corrosion consumed the aluminum. Decades of weathering erased the physical evidence. Today, almost none remains. A few bundles survive in museums, displayed alongside radar sets and night fighter artifacts. Visitors see the crinkled foil, the precise dimensions, the simple packaging. Most pass by without stopping. It looks too mundane to matter. But those who understand the history pause. They recognize that the mundane object in the display case represented a turning point. Not a dramatic one, not a single decisive battle, but a persistent, cumulative effect that altered the course of a campaign, and perhaps a war. The strategic implications extended beyond 1945. Window demonstrated that capacity warfare, overwhelming adversary systems through volume rather than sophistication, could be decisive. Modern militaries apply this principle continuously. Chaff, flares, decoys, jamming, cyber attacks, all aim to exceed adversary processing capacity. The means grow more complex. The goal remains simple. Force the enemy to handle more information than they can process. Create decisions they cannot make in time. Saturate their networks. Blind their sensors. Paralyze their response. The concept traces directly to those first bundles released over Hamburg in July 1943. For those who served, Window was a tool. For historians, it is a case study. For engineers, it is a proof of concept. For strategists, it is a lesson in asymmetry, how simple countermeasures can neutralize expensive systems. For all, it is a reminder. Even the most sophisticated defenses are vulnerable when adversaries think creatively about capacity rather than capability. The foil has long since dissolved. The radars are museum pieces. The veterans are gone. But the principles endure. The invisible weapon that blinded Hitler's air defenses left a legacy more lasting than the physical strips that fell across Europe. That legacy persists in every electronic warfare system, every radar countermeasure, every capacity-focused strategy employed today. The experiment begun in July 1943 never ended. It evolved. The evolution continues. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.